you would write this as y to the nth plus the nth minus 1 derivative plus, say, the n minus 2 dot 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 the first derivative, and then the function, and then this is equal to 0. That's one part. Now, these things, as a general rule, you can assume that the first one is going to have coefficient 1, but then each of the other derivatives of order smaller than n, in general, you would write something like p sub n minus 1 of x, p sub n minus 2 of x, okay, p sub 1 of x, and this will be p sub 0 of x. Each of these expressions, p of x, is a coefficient. This is a general form. Now, if those expressions are assumed to be constant, then that we're kind of back to what we discussed earlier today. So we could write this left-hand side, we could write this as a summation of p sub j of x times the jth derivative of y, and this index j goes from 0 to n, and this being equal to 0, where the nth coefficient here, p sub n of x, is assumed to be 1. If we do this, then we're basically saying here that this left-hand side is a linear combination of derivatives of y. Okay, so I'm going to call this star. These things, I'm going to call that star. That would be a way of expressing the higher order linear ordinary differential equations. By writing the coefficients as p sub j of x, those are just coefficients in terms of the independent variable. They may be constant, they may not be constant, right? But this is part of the homogeneous, the formulation of the homogeneous problem. So now let me say something. So what about let me run the next page. So let's consider this theorem. Suppose we have functions, n functions. Suppose that y sub n, y sub 2, y sub 3, all through y sub n are, notice that these numbers here, 1, 2, 3, 4, all the way through n as in number, they appear as sub-indices, not super indices, sub-indices. Each of them is a specified function. Suppose these are functions that are solutions of the homogeneous equation that I was calling star. So each of those, the derivatives of y1 all the way to order n, when computed and plug into that equation that was called star, excuse me, that function y sub 1 satisfies, it makes that linear combination to be 0. And the same can be said for y sub 2, y sub 3, all of them, okay? So if this is true, then this linear combination of these functions, where k here runs from 1 through n, also solves that homogeneous equation, where c sub k is a real number. Well, it could be considered a complex number in general. So what this theorem is telling us is that if you have several solutions of that homogeneous problem, the linear combination of those solutions would also be a solution. Okay? Now, the approach we're going to take is consistent with the approach of the homogeneous problem for second order with constant coefficients. Let me say something more about characteristic equation. Okay, so we set the solution to be of the form e to the r x. Then we compute, say, the mth derivative of this function. This is for every m and all the values there that we have. And then we replace these derivatives in differential equation we're solving, which is I call here star. Now, note, little bubble thought here, that these higher order derivatives, for example, the jth derivative, if you're assuming that y has this form, first derivative is r times e to the rx, second derivative is r squared times e to the rx. So the jth derivative here would be something that looks like r to the jth power e to the rx. This is an implication of taking derivatives of that exponential with argument rx, right? So if this is the jth derivative, that means that that linear combination this linear combination that defines this linear combination right here defines our homogeneous. These coefficients are constants, a sub j's. These derivatives here are now r to the j times e to the rx. Okay, so that means replace that into this. So that means that becomes a sub j r j e to the rx, and this is equal to 0. And j here is running from 0 to n. We're substituting this in that expression. The expression defined the homogeneous. So this is like, new equation, star equation. This expression e to the rx doesn't depend on j. So we could pull that. We could write this one more line as e to the rx times the summation a sub j r to the j. This goes from 0 to n, and this is equal to 0. That exponential will never be 0. So we can work here with only this part, right? We have the product, two things, to work with the summation, aj, rj. This starts at 0, ends at n, and this is equal to 0. That is a polynomial in R. The a sub j's are assumed to be constants, the so-called constant coefficients. Now this is now a polynomial in R of degree n. Polynomial of degree n in R. R is the variable of that polynomial. Let's take a look at this point. This polynomial is then the so-called characteristic equation. Let's take a look. Let me rewrite that summation, right? So let me write the 0 on the left side, and so 0 of the summation a sub j, r sub j. J runs from 0 to n. This is a0, r0, a1, r1, all the way through, say, a sub n minus 1, r to the n minus 1, plus a sub n, r to the n. Well, I can write the right-hand side, so I have here 0. I can write the highest power first, and part of what we're assuming here is that we're assuming that a sub n is equal to 1. Okay, that's the coefficient of the leading derivative, the highest order derivative. We're assuming that coefficient to be 1. So I can write the highest power first. So this would be Rn plus I sub n minus 1 R to the n minus 1 all the way down to a sub 2 R squared, a sub 1 R plus a sub 0. The big deal here is that we want to solve this for R. In other words, we're finding roots of n degree polynomials. In general, a polynomial of degree n has n roots. And in general, those roots are complex numbers. Okay? So there are that when I write E backwards, that means it's almost like ETSU. I see somebody here wearing the colors, another person wearing the colors. It's almost like the ETSUE, but it's backwards. Okay? That means there is or there are. So this is there are n complex roots of an n degree polynomial. Let's say let's call those roots R1, R2, R3, R1 bar, R2 bar, R3 bar, all the way through R sub n bar. Now, in some cases, this is where, in some cases, the imaginary part of some of these R bar sub k is equal to 0. Such cases means that the roots are purely real. They lie, they are in the complex plane, but they are on that horizontal axis of the complex plane. Also, in other cases, sometimes roots are repeated. Sometimes roots are repeated. We mentioned something about that when we had a polynomial of degree 2. And so sometimes they're repeated. Okay, so what then? When there are k repeated, meaning k with imaginary part equal to 0, so k repeated real roots, then solutions to that homogeneous problem with a sub j's with constant coefficients, then those solutions are things that look like this: x0 e to the r x, x1 e to the rx, x2 e to the rx, x3 e to the rx, all the way through x to the power k minus 1 e to the rx. So when there are k repetitions, then these solutions go all the way to the power k minus 1. And the linear combination of these things, xj e to the rx, when j goes from 0, when j goes from 0 to k minus 1, this is considered the general solution.